watch it. Okay, sweet. So when we look for poison materials, these are typically things like boron or hafnium. They're going to be, with a very small amount of material, able to remove a lot of neutrons from the ability to create fission. When you start removing those rods, less and less neutrons end up going into that poison material, which means a whole lot less of them are parasitically captured, which means they're able to end up in the fuel, which means you're able to create more fission, which means you create more power and more heat. So by inserting or removing that poison material, you directly control the fission reaction that's going on in your core. The reactor here on campus does something somewhat unique. You don't see this in commercial reactors very often, but their rods are backwards to this. Their rods have a fuel material in them. And so when you pull the fuel rods out, there's no longer enough fuel close enough together to create a fission reaction, because your neutrons, even though they'll transmit in between different pieces of fuel, they don't travel very far. You have to have enough material close enough together to get criticality. And when we take our criticality safety training, you'll learn about mass and volume and shape and how it affects that critical reaction. But essentially, as they put in their fuel rods, they're adding something called reactivity. So reactivity is a measure of how much our power we can produce, how much fission we can keep making. And so as we add reactivity, we've now created enough neutrons and enough fuel in one place to create a critical reaction. And if we remove some of that fuel or space it out a little bit, we no longer have enough present for all of that. So typically what you see is the poison rod. This is how our commercial reactors in the United States work. This is how most of our research reactors work. But every now and then you'll see something unique. The AGN reactor on campus, the zero power physics reactor that used to exist at INL. They had subcritical masses separated by a table, and they push them closer and closer together until they're just almost critical in order to do some experiments and measurements. And we'll get to look at a 1/over implot in a subcritical assembly here on campus when you guys do your reactor theory class. And it's the same concept. You're trying to put in material to get enough neutrons to have a criticality. It is, yes. Okay. When we're talking about control rods, especially poison ones, you have to be able to insert them within a specified time. When you're starting to look at an accident scenario of a runaway neutron reaction, there's a concept called doubling time that operators have to be aware of, which is how many seconds it takes for your reactor to double in power. We want to design reactors and operate reactors so that they have a longer doubling time, milliseconds to a few tens of seconds. This is something that you as a person can respond to in time to make a decision if the power level is increasing too rapidly. Criticality tends to build on itself. And so if you insert a very large amount of reactivity, say that you pull out all of the rods too quickly, and that reaction starts to go supercritical and power starts doubling very quickly, it will continue doubling faster and faster. You have a runaway reaction. In order to ensure that you can still shut a reactor down that's in that condition, which there's lots of other controls to ever prevent us from getting there, but let's say that that's all failed and that you're a bad operator and we have that condition, rods have to be able to drop in a certain amount of time, usually within a few hundred milliseconds. When we talk about drop, a lot of times a gravity powered drop is not fast enough to shut down the reaction before we reach the power level that corresponds to the temperature that will melt our clad, right? Because we're controlling power in order to control temperature in order to not release radiation, right? So many times, even though we might use this gravity-assisted drop, especially when we're talking about our pressurized water reactors, we'll often have a spring or some sort of mechanical force that helps ensure that that occurs quickly enough. When we're talking about boiling water reactors that push in from the bottom, the same thing, their hydraulic system has to be able to activate within a certain minimum amount of time between when they receive a signal and those rods need to be in. Yeah. It can depend a little, but usually at least double redundancy is the rule. And typically, in order to be able to stay operating, most places will have 3 or 4. Because that way, if one goes out and one needs maintenance, they've still met the 2 that's the rule, right? So just depending on how important a system is and how expensive it is to maintain, you might have increased redundancy just to ensure that you don't have to shut down whenever you have a maintenance outage or a repair with those. So at least 2 is the rule. More is generally what's seen. So here we have this control rod that goes right in the middle, right? It's essentially a cylinder that fits down. Here we have more typical control blades that we see in our boiling water reactor. And this would fit down this cruciform across the quadrants of your fuel bundle. Either style that you use, you still have to be able to drop them down. Then, once you get them in your core, you also have to be able to certify that they will stay in the core and maintain shutdown. And you usually have to do the calculation, the engineers have to do the calculation to show that this design works, even if the most worth core control rod is stuck out of the core. This is called the stuck rod criterion. Rods typically do not move one at a time because you have hundreds of them. You have control rod banks. And so you might be moving a set of 4 or 10 rods at a time, somewhere in there, sometimes more, sometimes less. And they're arranged across the core in a pattern that as you move the banks in order for your procedure, you are maintaining a very even distribution of flux across the core. You don't want one part of the core producing more neutrons than another part and creating hot spots, right? You want it very even. So as you move these banks, they are designed to create even flux. And so if for some reason the mechanism of one whole bank stops working and you can't insert those rods, you have to be able to prove that your reactor will shut down and stay shut down with those rods stuck out of the core. This is a concept called the shutdown margin. That's how far below critical we can keep the reactor and ensure that it stays shut down. And the rods being out of the core that you have to calculate this with is called the stuck rod criterion. So not only do you have to ensure that structurally they're not going to shake out of the core with an earthquake, but physics-wise and reactor theory-wise, they have to be worth enough to keep it shut down, even if you don't have some number of them, okay? We talked about this, right? We can have pneumatic, hydraulic, or mechanical systems, and they're usually assisted by gravity. So what we would say with a boiling water reactor is that we have a gravity-assisted hydraulic control rod system, right? Yeah.
So that was boiling water?
Yes. Okay. Because we're going to have to actually insert them from the bottom, right? Because the top of our core has our steam and our boiling liquid.
So it would still be gravity assisted if it's being pushed up from the bottom?
Yes, because the way you design that system is you're going to have imagine like some sort of plate. And when you need to insert your reactors, you're going to drop like water or a hydraulic lever on those, which then push them up, right? So you're still getting some gravity assistance, but then that is activating a mechanical system that pushes them up, right? So engineers still want to use gravity as much as possible because we're pretty sure gravity is always going to be there. And if it's not, honestly, we have bigger problems than our reactor accident, right? So gravity can be a consistent force. So whenever they can use that in the safety system, it's automatically there. It's passive. You want to. So even though we're pushing in from the bottom, we still use gravity push that mechanical motion. Make sense? Okay. Okay, so let's switch a little bit. Let's talk about emergency core cooling systems, the ECCS. You will need to know this acronym for the rest of your life if you choose this career. It's very common. Emergency core cooling system. Okay? So there's a primary coolant system, okay? Its job is to convert the heat from fission into steam. And it goes from the core to the steam generator. So whether that steam generator is inside your pressure vessel at the top of your core in a boiling water reactor, or if it's in a loop just outside your pressurized water reactor, there's some primary loop. The primary loop is contaminated radioactively, okay? There's a secondary coolant system, and it converts this steam into electricity. So it goes from the steam generator to the turbine. In a boiling water reactor, this is also contaminated. In a pressurized water reactor, it is not. Okay? In order for those two systems to perform their functions, there's approximately 100 different support systems at your average nuclear power plant. And these span from auxiliary systems to systems that help improve efficiency, to systems that control the chemistry of the water, to our emergency backup systems, okay? The emergency core cooling system only is used to mitigate the consequences of accidents. You have to test it and maintain it and keep it ready to actuate at any time, but you will hopefully never have to use it, right? So this is one that's interesting as we start talking on Wednesday about maintaining systems and controlling systems. This one has to be treated like you need it at any moment, and every moment of your operation, it has to be ready, but you hope that you never use it. So it falls into a lot of odd categories of having to be very highly maintained, but then we have some system issues where it isn't actually activated very often, right? So how do we prevent valves from getting stuck or pumps from getting corroded and not turning on as efficiently as they need to when we don't really use this system? And one of the answers is we're going to test it regularly, but it's a unique system engineering problem, which means it's a unique operations problem for you guys to be part of that maintenance and testing. Okay, so let's understand the ECCS a little better. So we see this picture, right? We have our reactor, we have pumps, we pump that to our steam generators, and then we have a pressurizer, right? So this is a 2-loop Westinghouse PWR, okay? ECCS is going to provide core cooling to minimize fuel damage following a loss of coolant accident. A loss of coolant accident, or a LOCA, is something we'll learn about in detail in your last semester in our reactor steam supply systems class, or Thermo 2 class, essentially. But essentially, you can have large break or small break LOCAs, which are either a leak that is removing water so that you're having trouble keeping the top of the core covered, or a large break LOCA that essentially somewhere in your primary coolant system, you're losing significant water to the point where you're not able to make it up. You're not able to put water back in at the rate you're losing it, Okay? In addition to this pretty obvious emergency core cooling, providing cooling, ECCS will also provide extra neutron poison to ensure the reactor remains shut down following the cool down associated with the main steam line rupture. So essentially, that poison material we talked about being in our control rods, something like boron, boron can also be in a liquid solution. And so we can also put borated acid into our coolant in order to help provide more shutdown margin, right? So if we have some issue with ensuring that we're staying shut down, this provides another method to add poison to the core, okay? Okay, so if we have a LOCA and we need to provide our cooling, we need to inject very large amounts of cool, borated water into the reactor coolant system. So we're still assuming that some parts of our primary system, like the pressure vessel itself, can hold water, right? In PWR, there are 4 separate systems to do this, and each one of these has to have some redundancy. So not only are there 4 separate systems, but you might have 2 trains for every single system, sometimes more, okay? There's a high pressure injection system, an intermediate pressure injection system, and the low pressure injection system. There's also the cold lake accumulators. All of these systems have to be able to operate when normal power supply at the plant is gone. So they're all going to be powered from whatever the emergency power system at your reactor power plant is. Typically, most commercial power plants have a backup diesel generator system with very large diesel engines. ATR and INL just switched to a battery-backed system, which is a little bit new, but there's a lot of EPA regulations when it comes to these huge backup diesels. And because we have to test these, we have to turn them on so many times a month for so many hours. And during that time, you're essentially creating some pollution that you have to pay for. It's just the way the EPA works. So a lot of plants want to go away from this, but it is currently the standard in reliable, on-demand backup power. Okay. One interesting thing, this low pressure injection system, this is essentially assuming that the pressure conditions inside the reactor have degraded, right? So it's no longer held at a pressure. And you hope that this occurs when you've cooled your reactor enough from its initial power and heat condition that you're just dealing with residual heat removal. This was one of the big things at Fukushima, right? So it sounds like residual heat removal is not significant, but after a reactor stops creating fission, just like your campfire, after it stops creating flames, still has residual heat in the coals. The nuclear fuel is the exact same way. You still have heat, okay? And so this has to be able to continue to provide cool water to remove that residual heat. So if this is our containment, okay, here's our reactor coolant system. Cold lake accumulators are here, right? So essentially they collect some water from the cold water piping that comes into the core, the inlet. And so they can add more water as this water boils or leaks out, right? You got cold lake accumulators. You have an additional storage tank for your emergency backup water systems, okay? You got high pressure injection system. So this system itself is high pressure. So even if the pressure is building up inside of here and it wants to resist somehow our injection, this high pressure injection system can still inject and spray. intermediate pressure injection system, okay? And then we've got our low pressure, which essentially has its own emergency heat exchanger that allows us to continue to deal with residual heat. And this RHR is residual heat removal. Okay, and RCP stands for reactor coolant pump, steam generator pressurizer. I think that covers all the acronyms that are on there.
So, when it says cool fluoridated water, what does it mean by cool? Because the reactors are not such a
So typically, cool can mean about any temperature less than what the reactor's at. A lot of times, you don't want to put in actually cold water because just the extreme difference that can occur as you put that cold water in, especially if, you know, when we talk about BWRs in a second, you've got steam in there, and as you put that in, it's going to immediately condense that steam back into cold water, and you're going to have some big pressure changes. So typically, there is actually some heating in the backup water, but it just depends, right? If you lose your offsite power, you know, Fukushima, their cold water came right from the ocean, right? So that was 80 degrees rather than the several hundred degrees Celsius that it normally is inside the core. So it can vary. But generally, when we're talking about cool leg, it's actually still very warm. It's just cooler. Okay. And then just note, even though this simple diagram just shows one pump here, every one of these systems has multiple redundant pumps, right? We have to be able to count on these systems. They're going to have a lot of redundancy. And this is where a huge amount of the expense in the construction comes from, as these huge systems. Okay. So, emergency core cooling will automatically start injecting when you receive the right kind of emergency actuation signal. So if you get warning in the control room of a LOCA, or if you get warning in the control room that the core temperature is above a certain amount, this is going to automatically start occurring, okay? Essentially, it repurposes the pump. It takes water from a storage tank and puts it right into the core coolant, and it assumes that certain parts of that system are still able to pump into the core, okay? A high pressure injection system provides water to the core during reactor coolant system situations where the pressure remains high, okay? So this is a small break LOCA, steam pipe break, or leak through a steam generator tube, small leaks. You can maintain pressure, and then you're going to use your high pressure injection system. Intermediate pressure is somewhat redundant because when you get an emergency start signal, it's going to start pumping this, and you have relatively high primary pressure still, but you might be losing some pressure because you have an intermediate break instead of just a small break, okay? And then the cold leg accumulators, they don't require any electrical power. They're just very large tanks. They have a pressurized nitrogen gas bubble at the top of them. And if the pressure in the primary system starts dropping, essentially that gas bubble just pushes the water into it. So one of the things that's a little bit backwards is you might think the high pressure injection system is for bigger accidents because it's going to be pressurized, it's going to create a lot of force. It's actually for the smaller LOCAs because the core can maintain its own pressure, and so it has to be at that highly pressurized same level that the core is in order to inject, right? Our cold leg accumulators are actually our biggest accident safety system, because if you've lost pressure in your reactor vessel, you've lost a lot of water, that's when these will automatically inject without any power, without any mechanical system. That nitrogen gas bubble is just constantly pushing the water, and once the pressure in the reactor vessel is not sufficient to push back, that water just drops in, okay? So this is our large break LOCA system. And then of course we've got the low pressure injection system and our residual heat removal system, which deals with residual heat, okay? You've got its own heat exchanger. This is also called long-term core cooling or recirculation mode. So if you have some accident where you can't restart your reactor, put that primary system back on, but you need to keep it in a safe, cool, shutdown position, this is the system that's going to happen. Okay? There's also a fan cooler system and a containment spray system. Okay, these reduce containment temperature and pressure after an accident inside the containment building. So if our ECCS does not prevent an overpressurization or some sort of leak happens inside the containment building, we're going to force circulate the air inside contamination to try and get some cooling, right? Water's better, but we'll try to do it with the air. And then we have a containment spray system where essentially inside containment we'll spray water on the pressure vessel, okay? If the atmosphere inside containment would be filled with steam, and we're starting to pressurize containment, this is one of the things that happened at Fukushima, and we had these hydrogen conflagrations that blew the top off the containment buildings, right? They're little square buildings. By spraying water into that gas that's creating the pressure can then be condensed, right? You're putting cold water in contact with hot steam, you condense it down to a liquid, and then you reduce pressure, right? So this system is designed to prevent that kind of issue that they had at Fukushima, okay? And here's a picture of it, right? You have your core here and your containment building, and you're gonna spray cool water in, and then when you get that moisture that now condenses down at the bottom, you have a sump, and you'll pull that moisture out so that you don't have it heating up and creating steam and creating pressure again, right? And so you prevent that problem of creating an issue with your steam. Okay. It's possible that the NRC does not require every plant to use every single one of these, and some vendors might use slightly different names. So the names that I use, that I'm used to seeing, if you hear something slightly different, it's the same type of system. The NRC does regulate how many redundant safety systems need to be functioning, and it's based on how big your reactor is, how big your plant physically, the land, the acreage is, how big your emergency planning zone is, and what your postulated maximum accident is, okay? Okay. Any questions on pressurized water reactor emergency systems? Essentially, we're getting water to the core, regardless of what pressure the core is at, and then we're spraying water inside containment to prevent pressure from building up, okay? BWR has a high pressure coolant injection system, just like a pressurized water reactor. It has an automatic depressurization system. It has a low pressure coolant injection mode, and it has a core spray system. And then you have your reactor core isolation, okay? The reactor core isolation cooling system provides makeup water, okay? So essentially, automatically, if you have low water in your boiling water reactor, or if you as an operator decide that water is needed, our SIC system will pump in water from another storage tank, okay? It's technically not an emergency core cooling system because it provides makeup water, but it's important in the same way, okay? So here we have our poison tank, okay? We have our normal recirculation system, right? And here we're gonna get our main seawater line, okay? The high pressure coolant injection system is the more ECCS. It requires no power or external cooling water, and it's designed just like in a PWR for small and intermediate sized LOCAs, okay? It provides makeup water when the reactor is still at rated pressure, okay? The automatic depressurization system, essentially, if it receives a signal, it opens a bunch of valve actuators, okay, that will open those valves. It provides depressurization for events with small or intermediate LOCAs. If, for some reason, our high pressure coolant injection system is not available. So you have a small break, you have your high pressure injection system, but for some reason, you couldn't get your high pressure injection system to work, but you still need to deal with this emergency core cooling. So let's very, very quickly depressurize the system so one of our low pressure systems can work, right? And so this removes the need essentially for them to have that intermediate one as they just deal with the pressure, okay? Oops. Core spray, very similar to a PWR, okay? Except that we're gonna spray inside the pressure vessel and we're gonna spray water on top of the fuel assemblies, not just in containment, okay? And then that low pressure coolant injection system and our residual heat removal provides makeup water for cooling under lots of coolant accident conditions. There is a suppression pool underneath the BWR. It's going to essentially allow a lot of water access for all these ECCS, okay? It's going to operate automatically. We talked about that fuel cladding, right? So it melts somewhere up around 2200 Fahrenheit, a little higher. So this is the temperature that we have to keep the clad from reaching. So all of these systems are designed with that in mind, okay? This has multiple modes of operation at a PW, at a boiling water reactor. Yeah.
What temperature is the clad usually at?
Usually it's half that. Usually your limit where you start having to engage in some emergency procedures is at half that melting temperature. So you want such a margin of safety, and then your operational temperature will be down around 500 to 700, right? So when you get to about that 1000 or 1300, you're going to have to start activating operational modes to keep you from going up further in power and temperature, right? The reactor will do some automatically. Yeah.
So when talking criticality, do all reactors run at some sort of criticality? Because Chernobyl and Fukushima, they were at.
Yes. So every time you increase power, you're actually making the reactor supercritical. The concern is if you do it by too much reactivity or too quickly. As long as you are slowly going supercritical, you can control that and you can tell the reactor when to stop increasing in power. If you make a huge reactivity insertion in order to go up in power really, really fast, and you're super prompt critical is what it's called, now that reactor is no longer operating on a time scale that you as a human can control. It will increase in power so much so quickly that it will be run away before you can even realize the signals that are coming in. Sometimes before those signals can even actuate for you, right? So it can actually go faster than the machines you're using to monitor it can respond. So it's not that supercritical is in and of itself bad. We'll go supercritical every time we go up in power. It's that you want to make sure that you're only a little bit supercritical and that power increase is going slow enough you can still control it. Does that make sense? Okay. This low pressure mode is a dominant mode, but there's a lot of different modes this can operate in to create our continuing residual heat removal. Because again, once we've dealt with the immediate accident, we may not be able to restart right away, and you have to be able to deal with that decay heat that's coming off of the fuel. Okay. Any questions on those systems? Everybody online? Yeah, Brooke.
What type of reactor was the one at Fukushima?
I actually don't remember what they were. Let me look. I believe that they were boiling water reactors.
How many reactors were there?
There were 4 units at that plant.
And what was what caused the meltdown for that one?
The biggest thing was that they could not keep water on it because they were without power. They had a total station blackout for so much longer than was expected after having so many emergency and backup systems destroyed by the tsunami that they just couldn't find a way to jerry-rig a system to get water in consistently, essentially. Yes, it was 6, not 4, sorry, but 2 were already decommissioned. It was a boiling water reactor at Fukushima.
That was in 2010, right?
Number one, actually.
2011, yeah.
Yeah, 2011.
Yeah. And it's interesting because, you know, that changed a lot for the nuclear industry. And we talk relatively little about the great success of the 2 reactors in Louisiana and the reactor in Mississippi that survived Katrina, right? So, and that was a huge loss of power event for those plants as well. And I do think that the tsunami in Japan was several scales more devastating than Hurricane Katrina was for the United States, right? Because our major damage was limited to a small region of the country. So we had a lot of support infrastructure that could come in and aid. Whereas in Japan, it was the whole country that had a lot of devastation, right? That's very different from a response point of view. But like we have reactors that can withstand this type of damage, and the containment and the core at Fukushima also withstood the earthquake and the tsunami. They just didn't know to expect to have that many days of a total station blackout with no help coming and all of their systems being damaged, right? If any one of those things had been slightly different, I don't think we would have had the issue we had at Fukushima. It's just that all of those things happened at once. Because systems are so designed to be redundant, right? Okay, any questions from anybody online?
Nothing so far.
Okay. All right, well, we're done for today, and we will continue our discussion on essentially control of safety systems. There's a DOE order 420. I do recommend that you have a copy of Chapter 5 with you because we're going to look at some of the regulations. So if you prefer to have things printed out, you might want to print it ahead of class. Otherwise, electronically is just fine. Okay, I will see you guys tomorrow for lab.